Let's utilize some software from our friends at Finner Dunlop. Daryl's going to be so kind to allow us to use his proprietary Belt Wizard software. And let's run some scenarios on some known conveyors just to show you how this works. So here's an example. We'll use a conveyor system that I'm familiar using and working on. This is Jamaica. It's a 7,300 feet of conveyor belt, 42 inches wide. It goes from the top of a mine at a bauxite operation across the mountain range, down a valley, across a road, onto the shipping point, loading point in the ocean. Bay of Discovery, where Columbus discovered the New World, right? Right at that point. So we look at this and we say, okay, this particular conveyor system has about 80% tension across this mountain point. It's about 60% tension at the tail. So it isn't a real high tension application. We don't see a lot of force on this at all. About 60% at the head. So it isn't a crazy high tension system. We're not seeing the head and the tail 100%, 120%, you know, pretty standard stuff. Let's go up to the transitions. We see we have the tail roller circled, so we have that profile now shown. This is a cross view of this belt, the forces applying to this conveyor belt. Just like I drew here, we can see those forces within that conveyor belt fabric widthwise. So here's the center of the belt, here's the edge of the belt, 100%, 0%. Clearly at this dimension, 75 inches, fully troughed to the tail, very well in the spec. It's 75 inches now. Let's change it to 65 inches. Do you see the shift? A little more tension, that 10 inches of distance. Now we're up to 100% on the edge. Let's shift it 10 more inches. That's 20 inches we've changed the tail roller transition on this conveyor. And we're 112, 115% on the edge, still about 40% in the middle. There's 30 inches, we've moved the tail roller. And in 30 inches, we're breaking the edges of the belt, overloading the edges, damaging splices, pulling up clips, fasteners. Let's go 10 more. That's 40 inches of distance. At 40 inches of distance, we're getting very close to that compressive zero number in the middle. That's the big no-no, right? And of course, we're way over tensioning the edges, really breaking the belt down. Now, let me just switch real quick screens. We'll go back to this. So you look at this a second. Look at this photo. How far apart are load-carrying idlers, troughing idlers? On average, in a typical system, nothing special. 20 foot apart? 5 feet? 4 feet. You'll find that the average system, especially, you know, kind of a standard off the run-of-the-mill system, the load-carrying idlers are about 4 feet apart, the troughing idlers. The return idlers might be 10 or 20 feet apart, depending on the system, but most of the load-carrying idlers in that range. So for point of discussion, let's say 4 feet. So now, in the booklet, we're describing there should be some transitional idlers. When we look at what a transition zone is, where the belt goes from flat to fully troughed, in other words, flat to 35 degrees, along that length, and it might be several feet, it might be 10 feet, right? So along that length, we have to have some supporting idlers to support the weight of the conveyor belt so we don't damage the fully troughed idler from the load on those bearings. We have to have some 20 degree, 19 degree, whatever, 27 degree idlers along that length to support the weight so the product doesn't spill, doesn't damage the edge, right, to control it. We don't measure those idlers in this equation. We're measuring that transition distance, we're measuring from the center of the tail roller to the first fully troughed idler. If the entire conveyor system is 35 degree troughing idlers, you're measuring from the center tail roller to that first 35 degree center to center. That's your transition distance. Everything in between you don't worry about, is just holding the weight of the belt. Now, since load carrying idlers are about 4 feet apart, and transition idlers are very lowly, right, very 19, 27 degree, real small, not highly angled, right? And your third shift, it's a maintenance guy, it's late at night. Maybe you're at a place out in the desert and this place is really cold, especially at night. Maintenance guys go out and they find they got a bad bearing on an idler. And the guy says, you know something? It's way back this catwalk, way back down to the chute, back to the supply shop to get another idler. Hey, I'm just a maintenance guy in third shift. What do I care? An idler is an idler. They're all the same. I happen to have an idler sitting on the catwalk somebody left from some other job. It's a 35 degree idler. I don't know. I don't care because I don't know the difference. I don't know what questions to ask. So I slap in a fully troughed idler, maybe even a 45-degree troughing idler, and I slap it in about 20 inches away from the tail roller. Could you imagine the extreme forces we're putting on the conveyor belt? That's what happened in this case. The guy had a perfectly operating conveyor belt. This perfectly operating conveyor belt ran fine. Conveyor belt worked, splices worked, everybody's happy. They switched this out. They had a huge amount of stress in the splices in the middle from this compressive force, but it didn't really show. They were there, and it was breaking the belt down, but nobody really noticed it until the first what? Cold snap. So out in the desert, it's a night, first cold snap of the year. It gets pretty cold, right? And this first big cold snap, the guy calls up the next day and says, "Holy moly, Mr. Distributor, get out here right now. Oh, I got 7 splices. Every one of them are coming apart in the middle. I'm afraid the belt's going to pull in two, and I'm mad. We're calling our lawyers. You screwed us. You sold us a bad belt, and you did bad work." Forget that the belt worked perfectly for 6 months in advance or a year in advance, right? Not a problem. But that first cold snap with a change in this transition distance. So let's go back to this software and see if you can think about what I did. How much distance had I changed? Remember, it was 75 inches, and I changed it to 35, right? One idler length, 4 feet, right? 40 inches. So within a short distance, by doing that one little switcheroo, taking the transition idler out and replacing it with a fully troughed idler, I shortened that distance up by 4 feet. I broke the belt. I'm breaking every splice in it, and the entire conveyor belt's cracking and tearing the edges. It's that simple. It's that simple to have happen, and it's that simple to have every day. And it's that simple for somebody in the field not to understand this process, and they just want to jam the chute right up close to the tail roller because of length, space requirements, whatever. And in the process of doing this, they're breaking their belt down, breaking the splices down, and it's your fault because you did a bad job splicing in his mind. In his eyes, he's upset with you. Well, maybe there's a reason that you should go in there and say, "Listen, let's ask the right questions, because I know what to ask now, and let's see if we can't work through this process and fix it." So we just reverse this out, go back to 75 inches. Now the load is much even, or even in the conveyor belt is a lot more stable. We can even lengthen it out more, 100 inches. Yeah, you can see it just starts to flatten all this stress. Now, of course, it's not practical to have an incredibly long transition length. Ironically, though, underground coal mining. Underground coal mining, some of you guys may not be involved in that, you may be, I don't know. How long a typical distance do you think they use in these underground, super high tension, really long conveyors? 60,000 foot long belts running 1,000 feet a minute underground, real high speed, 100% tension, really, these are bad boy belts, lots of them. Do you think they have a short transition distance? Oh, they have hundreds of feet. Because they have a lot of length underground, they overlap one belt on top of the other for the transfer. They might have 200 feet of distance in the transfer, or 100 feet of distance, trying to get all the strain out of the conveyor belt so it runs better through the system on the transition. So they understand that. These guys have been through this process already, understand the value of it. So now, that's the tail, and this is fully troughed. We've already determined what fully troughed is. Remember the head pulley. So at the head pulley, pretty commonly you'll have half troughed. Remember I told you they lift the pulley up on plates of steel, shim it straight up, right, vertically? In doing so, they're reducing some of the stress in the system. You can shorten up the transition distance that way. You can have a little shorter transition distance by reducing some of the stresses by lifting the pulley.
Does that only work on the head pulley, Mike?
You can do it in the tail as well, too. Just remember, you change the tail pulley height, now you're changing that impact, or that loading point. You could have the belt running into the chutes, the hoppers, putting more strain on the conveyor belt at the tail. You've got to take the whole picture into account. But if you need a solution for a problem, that's obviously a solution. So let's look through this. Let's work through this scenario. Here we are at the head. Same thing. We have head pulley, the transition length. Here's the stress of the belt seeing, the edge of the belt, the center, the edge. Notice that the center and the edge have the same force on it. You got this little dip, right? Right? And it's at 42 inches. Let's play with this number. Let's drop it down to 32. Start to see a shift. A little bit less force here. A little greater force in the middle and the edges. That's 20 inches. I moved the transition distance to the head pulley 20 inches, and now I'm really burning up the belt because I have two major problems. Now at the head pulley, because I shortened that distance up, this is zero. That's zero tension. So now the conveyor belt has areas in it at zero tension, actually a negative value, is compressive. So wouldn't I be pushing the fabric together, breaking the belt down internally, breaking the splices down here and here across the width of the belt? At the head pulley, about 112%, 110% tension in the middle, tension on the edges. So I'm putting a lot of stress on the edge of the belt. So think about this belt, the width of it, across the width of this conveyor belt in a very short amount of time. I'm putting 110, 115% stress on the edges, the middle, but down this one section, I have a negative value. Think about your splice, what it's doing to this whole conveyor belt, the stresses it's seeing. We'll draw it out. We'll show you. So let's take the same scenario, and then we're going to be able to talk about what Joe talked about a second ago. So now here's our conveyor belt. We have these real extreme stresses in the conveyor belt. We know that we're going to have this W-shaped stress in it. You see what a great artist I am. We know at the head pulley, we've already went through that. We've got to be pretty much stress-free so when that roller equalized across that surface. We're going to be folding fabric and breaking fabric. So in this scenario, what would I be doing at this point? When the belt comes in contact with the roller, same thing. We talked about it. Here's the belt coming in contact. Here's the head pulley. At that point of contact, what's going to happen right here and right here? Belt's elastic, right? The belt's elastic because it's being stressed and strained. We've got high stresses, little or no stress. At this point of contact, this has to catch up. So you're up to this conveyor system, you're walking around looking at this conveyor system, you hear this high-pitched squeal, you think a bearing's gone bad or something. Take a handful of rock dust or dirt, turn a water hose on, put a little lubricant, in other words, i.e. lubricant, on the belt as it runs, the squeal goes away within a second. So it's not a bearing, it's the belt slipping on the drive. You look at the lagging. What kind of representation would we see in the lagging? Would we see a real odd pattern in the lagging?
Who wants to answer that?
Take a shot at it. Bill, go for it.
Yes, there'll be more wear on the edges of the belt on the lagging.
Would it be the edges, you think? Think about the stresses.
Actually, it'll be in the lower
With the compression.
Yeah.
where the compression is in the two spots.
So here's our lagging.
That's where the belt is slipping on the pulley.
Right. So we have our diamond lagging, right? The lagging's, I drew this extreme so you can visualize it. We're going to be wearing the lagging down about, say, 8 inches, approximate 6 to 8 inches area is going to coincide with that. Because if the belt has to catch up, and the belt's trying to catch up and catch up, as it's going through that process, it's slipping. As it slips, it's wearing the lagging right down to the steel. So you look at this roller sitting there and you say, that's odd. The lagging's not too bad a shape in the middle and the edges, but you got these two sections that are worn right to the steel, smooth. Right away, that tells you, hey, I got a short transition to the head pulley. Only way that can happen. Short transition to the head pulley right away says, hey, wait a second, I mean splice problems. Right away I tell the customer, hey, I bet you got splice problems in that system. Let me help you fix them. Maybe you're not just put a little value into your selling that customer product, you know. You're not just another Me Too guy out there doing whatever. How many guys have seen that in the field? You seen it? You seen it? Nobody else ever seen that? Nobody goes in the field? Well, okay, so if you have the wear pattern in the dead center, so it's worn just right through the center but not the edges, would that be at the head or the tail? Depending on what kind of transition it is. Yeah, typically at the tail, right? And what would that tell you on the transition? There's a lot of stress in the middle of that belt through the transition, a skidding effect on it. Yeah, too short. Transition distance is too short. So let's look at the fully troughed transition length. We have to know the difference between fully troughed and half troughed. Once you understand that and you go in the field and you know what to look for, you can quickly identify what's what, right? So typically know, on average, the fully troughed is going to be at the tail roller. Pretty common to see that. If we have 35-degree troughing idlers, the entire system is made up of 35-degree troughing idlers. We know that the percentage of tension we're seeing in that conveyor belt, we've done the quick math in the field to say, hey, listen, this belt, it's running less than 60%, right, in this range. So it's not a real high-tension belt. So let's call it 60 to 90%, this middle range, just for purpose of discussion. We've calculated that in the field already. We know the transition idler size. We take the belt width times 2.4. Belt width times 2.4, it's got a 2.5, rounded off, right? You can use that software I just showed you that you can buy, or Fender has, different people have similar software. They calculate it to the inch if you need to be. But just in the field, real quickly, windage, hey, I need to have 2.5 times the belt width of the tail, and I'm going to be good. That's not to say that's the perfect answer, but you're going to be good 95% of the time. So right away, I'm saying, hey, listen, belt width times 2.5 at the tail, I probably will minimize this transition problem. Now, is that hard to figure out? Is that hard to go to the customer and measure that out and say, hold this tape here, Mr. Customer. Hold it at the center shaft of the tail. Let's go with the first 35-degree idler. Whatever that length is, belt width times 2.5, it better be the same answer, hadn't it? If it's not, you know right away, you're probably starting to put stresses on the edge. And at the head pulley, I'm going to show you how that works again in the software. Remember I was saying how we lift that pulley up vertically to get that half transition, all right? The forces across that belt a little more even. 35-degree troughing idlers, 60 to 90% of its rated tension the belt operates at. About 1.5 times belt width. So right away that tells you, hey, I can have a shorter transition distance. If I lift that pulley vertically by a few inches, I can shorten that up if I have to. I'm in a tight situation, I can do whatever. But I have to be careful because it's a double-edged sword. At the tail, or at the head pulley, with a half trough configuration, if I really jack it up too much, you get a little carried away with it, it works backwards, and I can have all these abnormal stresses. Let's show you an example. So the tail roller currently, it's at 100 inches. Let's change it back to 75 as the preset. And it's fully troughed, right? So pulley raised in inches is a 0, right? So let's change it. Let's change it to 2 inches. I'm going to lift it up vertically 2 inches to the tail. I'm starting to go into this half trough configuration. You see the stress is starting to change in the middle a little bit. 3 inches. Let's go to 4 inches. 6 inches. Now notice I'm getting really extreme. I'm really raising this tail roller up. Getting kind of stupid here. 6 inches. Look at the center, all the force I'm putting in the center of the belt. There's 10 inches. So I mean, yeah, you can be a little carried away to say, yeah, if 2 inches to 3 inches is all you need, 10 inches isn't better. I'm putting the entire full width of that belt tension right, funneling it down to one spot in the middle of the belt. Let's think about a splice. We'll start out with a vulcanized, and we'll move a flex. We'll put it into a mechanical in a second. So here's my vulcanized splice. Top joint, bottom joint, center ply butt, 3-ply belt, right? Think about how the stresses are going through that splice. Are the stresses even across the width of that belt for that splice? No way. So what I'm having is on the edge of that conveyor belt, a huge amount of stress inside the splice and that step area, that overlap step area on the edges, and compressive, very little forces in the middle. So if I have a 36-inch wide belt, what that really works out to, I could say on a 36-inch wide belt, as just a kind of a ballpark, that I probably will end up with about maybe 10 inches on either side carrying all the load. Right? As it goes through this transition, it's too short and it's a problem. I'm overloading the edges, so now my splice, instead of being able to put all those forces across the full width of that conveyor belt evenly, I have all my forces, and it's only rated, I'm only running 60% its rated tension, right? So we're not loading the belt up anyway. But I'm taking that 60% of its rated tension and funneling it down to 20 inches of belt width. Now I've got a problem. Now my splice is running way past its operating tension, way past the safety factor. If I don't do an absolute, total perfect job, you guarantee there's going to be a separation of the edge, there's going to be some cracking, some breaking. What's the chances of doing a perfect job every time? Especially if the belt's a little old. It ain't going to happen. So that's the reason you have all these additional safety factors built into it. You take this into account. Yeah, I got to be worried about that. Let's do the Let's do the head pulling. Here's our splice. Now, same thing, 36-inch wide belt. On the edges, I don't have a lot of surface area on that edge that's in force, right? It's in power transmission, a lot of tension. So I've got maybe 4 inches or so on this edge, maybe 6 inches in the middle, and maybe 4 inches in this edge. I'm trying to load all that force up on this 36-inch wide belt through that transition. And I've got a compressive value, a real low tension compressive value here. So here is the width of the conveyor belt. On this one side, I'm stretching the fabric and putting load and force on it. Just a few inches across from it, same layer of fabric, same plane, I'm compressing it together. So I got tension, compression, side by side as the belt goes through the drive, through the transitions. Would that work that belt apart pretty quick? Splice first, belt second, right? It's a gravitational force dragging it right down. That's right. This isn't hard to figure out when you go out in the field and just do some quick math. You'll find that probably half the belts you look at have a bad transition or questionable transition.